So good afternoon. Thanks for accepting this talk. What I'd like to talk about is the ETWA sounding rocket mission, with ETWA standing for the Equatorial Temperature and Wind Anomaly. And it's a mission that we'd like to fly, and I'd like to kind of motivate it with the talk today. So could I have the next slide, please? So what is the ETWA? And it's basically the neutral gas partner of the more well-known equatorial ionization anomaly of the ionosphere. It's a feature that straddles the magnetic equator near the dusk terminator. So unlike the EIA that has quite an extent in local time, this feature has only been seen in a narrow band of local time near the dusk terminator. The most comprehensive measurements of it were made in the 1980s by the DE2 satellite, and the primary literature appearing in the 1990s. So again, this thing has been unresolved for quite a while. There were even hints of it being measured earlier than that in some of the very early missions, but there weren't enough. There wasn't a comprehensive data set available from those missions, and they often had low duty cycles and orbits that were not conducive to measuring this effect systematically. So DE2 is the one that really kind of put this one on the map, so to say. So this is what you see on the right is a typical DE pass for over near the dusk terminator. I mean the dusk equator. And what we see top to bottom is it's in these color coding. We see, so the red dashed line here is the magnetic equator, and the orbits are roughly north to south here. So we're crossing the equator as we go from left of this fiducial to right of the fiducial in the magnetic equator. And so what we see going top to bottom is we see strong zonal winds. So this is expected that we see winds that are blowing from the day side over to the night side. But they're peaked at the equator, the magnetic equator, which is a little bit odd right there because, if this is neutral winds, how is the magnetic equator affecting that? Why is it organized by the magnetic equator? Moving down to the next panel, this is the neutral temperature, and we see sort of the inverse effect where there are temperature peaks above and below the magnetic equator. And then finally, in the bottom panel, we have downward vertical winds. So how does this picture all fit together? And that is the question. What forms this ETWA and how does it work? So the next slide, please. So the next time this was observed by a space mission was the Streak mission of the 2000s. And unlike DE2, which carried a lot of nice complementary instruments, this carried only a single instrument, a RAM pressure sensor. But it was in a dawn-dusk orbit, so it was going through this region several times a day, 13 times a day, or maybe no, more like 15 times a day. And so it got a good view of it. And so the data to the right show the measurements from the full mission here. And the top panel shows basically longitude versus latitude. So this doesn't have any local time information in it, but it's all at dusk. So this is basically a slice at dusk. And what we see is pressure. These are pressure residuals over basically what's left after you do a low pass filter on it. And what you see is these striated pictures where we have low pressures in the red and high pressures in the blue, and it alternates. And it's really sharply delineated by the magnetic equator, which is this squiggly line here. And so again, we see the idea here that this is a neutral measurement, measuring neutral gas, and yet it's organized by the magnetic equator. And for a long time, when I was looking through the data, at least, I couldn't figure out what was going on, and didn't really understand it until going way back into the literature and seeing what happened with DE. So the other data set here is sort of a different cut of the data, and this now goes from latitude. So this is basically the direction of travel of the satellite. And then as we went, we went through various altitude ranges as we were descending. This is basically a high drag region. And although we had some propulsion on streak, we didn't have enough to keep us up there perpetually. Anyway, as we descended, we see the strong signature here until we get to about 275 kilometers, below which it disappears. And again, this is in dipole latitude. So when you see things that are vertical, they're all at the same magnetic latitude. Again, showing the magnetic control of this feature. This we went through in the paper here, this one from 2008, and we basically deduced that these were due to in-track winds. So basically, these are meridional winds that we have here. There are two things that can cause these kinds of perturbations in our pressure sensor data. One is the winds, and the other is changes in the background density. And so usually when you fly an instrument like this, you're looking at changes in the background density. But the more we looked at this, the more we understood that there's just no background density feature that can be explained like this, whereas explaining the winds explaining it with the winds is a much more tractable approach here. And so what we have here is that these winds they're going back, they're emanating from the equator, going poleward from the equator. That's the color coding here. And actually there's a second little sort of echo here. And so that's all in this paper, but it shows the ETWA, what's happening. And essentially what we have here is, if you remember from the previous slide, we had only the zonal and the vertical winds. This is now adding the meridional winds because DE2 didn't make the meridional winds measurement. But putting these all together, we think we have a coherent picture. And so this is what should have been seen by DE2 had they had that measurement. And the other thing to note is that these winds are quite strong, several hundred meters per second in this isolated range. So all of this has really piqued our interest into trying to understand this more. And so we'd like to fly through there again. I'll say we did have a CubeSat mission that was focused on looking at this had two instruments, essentially this RAM pressure sensor plus a Langmuir probe to look at the plasma data. Unfortunately, that mission didn't end up in the right local time, and so we never got anywhere close to measuring this particular feature. So again, it's remained elusive for various reasons, and we'd like to kind of go there with a rocket and see what we see with much more comprehensive measurements. So could I have the next slide, please? So there has been some theoretical work done on this, and basically the work that sort of is what I call leading potential explanations falls into three categories. So all of them, of course, the neutral gas being structured by the magnetic field is really a smoking gun that says that ion neutral coupling is expected to play a central role in all of this. So the physical mechanisms that have been put forward are these three. So the first, which is by Raghav Rao et al., who actually did the original DE2 work, is basically it's caused by breaking of the winds by ion drag. So if you consider these zonal winds here represented by this arrow, and then this little crest and valley thing, this is meant to be the EIA. So if I have winds that are trying to drag neutral gas across this, what we're going to have is we're going to have more collisionality under these EIA peaks because the plasma density is higher. And so what that's going to do is that's going to heat up the neutral gas, and it's going to cause it it's going to cause this basically a pressure bulge above the equator and below the equator. And if you look at what that pressure bulge then does is it drives the gas up, and it can create a little meridional circulation pattern, both to the south of the magnetic equator and to the north of the magnetic equator. So this is seen in the DE2 data, right? I mean, we see this picture of the zonal winds that are faster at the equator than they are at the above and below. That's because it's being braked above and below. And we also see the downward winds here at the equator here. And of course we see the temperature bulges. So this mechanism seems to explain it quite nicely. It would help if we had the the meridional winds to sort of put the cap on it so that we could actually see this vertical circulation pattern. Another idea by Fuller-Rowell et al. Is that, yeah, there's a lot of plasma here in the EIA, and so we expect to have enhanced recombination there. So we just have simple heating by this recombination producing heat and causing the same sort of thing, causing the temperature to increase, which creates a pressure bulge, which then can create the rest of the stuff. So in this case, the neutral wind is not really so much a part of it. It's really the chemical energy of the recombination that's always there. And I guess I would question a little bit whether that's the case, because if that were the case, you probably might see it at places where there's not much zonal wind. In other words, more toward the day side, and it's not really seen there. So that's one thing to check out, is to see if all the ingredients are there for each of these mechanisms. And then finally, Maruyama et al. in 2003 put together a model that said that this could be caused by field-aligned ion drag. So the idea is that the ions would be moving along the field. So that's north to south, or I should say, just say in the meridional plane, and that then puts enough friction onto the neutrals that it brings the neutrals up into the higher latitude regions, basically very similar to the ion fountain effect being involved in pushing the neutrals around. And so these are the three things that are of highest, I would say, potential in explaining this. And so that's what we'd like to go and figure out with a rocket mission. So could I have the next slide, please? Okay. Oh, is that the next slide?
So next slide, please.
There we go. Thank you. So so we'd like to resolve the physics here with a rocket.
Yeah.
Excuse me.
Sorry, a couple minute warning.
Okay, thank you very much. This is my last slide. So basically what we'd like to do is just what you think we'd like to do, which is we'd like to take a comprehensive set of measurements that cover the neutral gas in these categories, the plasma, and the electric and magnetic fields. And we'd like to take a rocket and launch that from Peru or some similar place that would be able to cover a fair amount of latitude across the magnetic equator. And so here we'd be launching basically right at the magnetic equator, but we'd be able to see a couple of these basically convection rolls that are predicted by at least the first model. But they're basically the structure that's seen by DE2, we would be able to cover with a mission that went kind of like this. It is a little bit difficult trajectory because we have to go a long way, and we have to get above 275 kilometers for the sweet part of it. And so the most straightforward methodology is to use a single Black-Brandt 12 with a tailored trajectory. So this blue area would be where we get our primary measurements here, but we would go several hundred kilometers downrange to do this. And there are other ways to do it. You could do it, think of two simultaneous rockets that had good instrumentation, one sort of a shallow trajectory, the other sort of a vertical trajectory, to also try this. But the one that we favor is the single Black-Brandt 12, which I know wasn't really approved for Peru for this time, but things can change, but we're also adaptable. So that's really all I have. Could I have the next slide? That's it. So thank you for your attention. I'd be happy to entertain any questions people might have.